Section 1.10 is modeling with functions. This is just some examples of a few word problems. So we'll go through the book. Make sure you have your textbook open to look through these examples. The first situation is when we are comparing two different situations, like example 1. Oops, excuse me. Pen here. This would be example 1 on page 253. And you did this type of example when you were in algebra. So we have plan A for long distance carriers, and plan A has a monthly plan with a fee of $20 flat rate plus 5 cents per minute for long distance calls. This is a little obsolete. We don't usually pay for long distance anymore. Plan B has a fee that is monthly fee is only $5, but they charge you 10 cents per minute. So two different fees, both with a flat rate and a rate of change. Hopefully you know that if you have a unit like dollars per minute, that if we multiply this by the number of minutes, we will get the number of dollars. So plan A would be 0.05 times x, which is the number of minutes, plus the $20 will equal the total cost. And plan B would be 0.10x for the number of minutes plus $5 would give us our total cost. So let's call plan A f of x, 0.05x plus 20, and I think the book uses t for time, and g of x for the second function. And we want to find out when these two functions, or excuse me, that's a plus, when the cost of these two functions would be equal. In other words, how many minutes? Obviously, if I'm going to not talk any long distance minutes, plan G would be better. But at some point, the more minutes I talk, plan F will be more reasonable. So we set these equal to each other. 0.05x plus 20 equals 0.10x plus 5, and solving for x, I get 15 equals 0.05x, and x equals 300. So 300 minutes is the time when these two plans will equal each other. This is a fairly simple kind of problem. It's a linear equation, a constant plus a rate of change for each plan, and setting the plans equal to each other. This example, example 2, in your textbook is a little bit tougher. We haven't looked at something like this. We're talking here about revenue, and in this case we have to put one model or one equation into another. So if you'll read with me about example 2. We're on page 255. On a certain route, an airline carries 6,000 passengers per month. So I'm just going to write that down as I read. Passengers per month. Each paying $200, so that's $200 per passenger. However, a market survey indicates that for each $1 increase in ticket price, the airline will lose 100 passengers. So as the ticket increases $1, we're going to lose 100 passengers. Now the question is, when is it better to increase the price, get a little bit more per passenger, or when are we going to have to, if we increase it too much, at some point we're not going to have any passengers. So letter A says express the number of passengers per month n as a function of the ticket price x. So we want to do n of x, the number of passengers, as a function of price. Well, the price is going to be x, will represent the ticket price, because that's what's going to change. Well, we know that we are going to have 6,000 passengers minus 100 passengers for every dollar that the price goes up. So minus 100 times a $1 increase. Now, how am I going to write that? Well, the ticket price might be $201, or $210. The ticket price is going to vary. But if I take X minus the original $200, so the new ticket price minus the $200 ticket price, that's the difference, or that's how many dollars the price has gone up. So hopefully you can see that if I raise the ticket price $1 to 201, then I'm going to lose 100 passengers, 100 times the difference. If I raise the ticket price to 210, then I am going to have 100 times 10, and I am going to lose 1,000 passengers. So that's the number of passengers based on how I affect or how I change my ticket price X. So that's part A. Part B talks about revenue. We have to understand that revenue is just the income that we make. It has nothing to do with costs. So the airline's revenue is the product of the number of passengers, which we found here, times the ticket price. So express the monthly revenue, R of X, will equal the number of passengers, 6,000, minus 100 times X minus 200, and all of that needs to be multiplied by the price of the ticket. So our revenue is all of this times the ticket price. Now if I expand this a bit, I will get 26,000 minus 100x times x, or 26,000x minus 100x squared. And that's my equation for revenue. You can see that this is a parabola that's going to open down. In other words, at some point I will reach a ticket price where my revenue after that point on starts to decrease. Revenue and ticket price. Okay, so there's an example of where we have to do a little bit more work. We've got to figure out how many passengers based on an increase or decrease, and then we have to use that to find our revenue. And we want to find the maximum revenue here. Pull out your calculators, and we're going to use this last equation. I'm going to erase a little bit and put it in here. And I want you to put in y equals, and we're going to use this 26,000x minus 100x squared, and place this into your graphing calculator, and I want you to find the maximum revenue. So when you put this into your calculator, you should get a nice parabola, and if you use second calc max, you should get the ordered pair where you have a maximum value. Take a look and see if you can do that, and we'll look at this on the next one as well, and we will review this in class. So if you can't get the calculator work, we will get with it together in class. The next one is using formulas. So look at example 3 on page 256, and let's read together. At the very bottom it says, a machine produces open boxes using square sheets of metal measuring 12 inches on each side. So I've got a square that's 12 by 12. The machine cuts equal sized squares from each corner. So it's going to cut out a corner here. And now we are going to look like this. And then it's going to take and fold up these corners to create an open-topped box. You can see the picture on page 257. So this is going to be a volume question. Volume is length times width times height. So we want to find V of X, part A, on the bottom of page 256. The volume of the box V as a function of the length of the side of the square cut from the corner. So in other words, this little value x, how much did we cut out of the corner? V of x. So my new length is going to be 12 minus 2x. It was 12 from corner to corner. I took out x here and x here. My width is also going to be 12 minus 2x, and the height, when I fold up the edges, is going to be x. Again, look at the picture in the book. It gives a very nice visual for that. If I expand all this out, turn off the video and try foiling this. Alright, if you got the answer of 4x cubed minus 48x squared plus 144x, you did a great job. We've got to think about domain here. The domain is the possible x values. X cannot be less than 0, because I have to cut something out of the box. What's the biggest square I can cut out of a 12 by 12? Something less than 6 by 6. So there's my domain. Again, try putting this into your calculator, using the domain of 0 to 6, pick an appropriate range, and see if you can get a graph. I'll turn off the video to do that. Okay, we should have gotten, and I set the domain at a little bit more than 0 to 6. I went 0 to 10. And I found that if I went up as high as, about 130, I could get the whole graph in. The maximum, in fact, if you use second calc max on your calculator, try that. You should have gotten 2, 128. Since the x value is 2, that means if I cut a 2-inch square out of each corner, I will have a maximum volume of 128 cubic inches. Our last example that we are going to do together, and we'll come back to this, is example 4 in the text, starting at the bottom of page 257. And it reads, you have 140 yards of fencing to enclose a rectangular garden. And we want to express the area A in terms of dimensions x. So we're going to do A of x, where A is area and x is a length or a width. So let's draw a picture. I'm going to call my width x. So I have x and x here. If my perimeter can be 140, then the length of each side is going to be half of 140 minus 2x. I've got to take 2x away for what I've already used for my widths. I have 2 lengths, so each of those is going to be half of the remaining fencing. In other words, my length is going to be 70 minus x. My width will be x. So, using a formula, area is length times width. Therefore, area here is going to be 70x minus x squared. And again, we can put this into our graphing calculator, find a max, and determine the maximum area that we can get for our garden and what dimensions it should be. There is one other example that I do want to look at, and it is example 5. And this one's a little bit more complicated, but again using formulas. A cylindrical soft drink can, okay, is to have a volume of 12 ounces. So volume has to equal 12, which is approximately 22 cubic inches. So we want to have this be 22 inches cubed for our volume. Express the surface area of the can. Well, we need to know what the surface area of a cylinder is. So a cylinder can be broken down into 2 circles, and then if we take and cut the sides and stretch it out, we get a rectangle. So the area of a circle is pi r squared, and I need 2 of those, plus this stretched out is going to be the circumference of the circle times the height. So I've got 2 pi r squared, circumference is 2 pi r times h. So that's my surface area in terms of r. So that's part A. Express the surface area of the can as a function of the radius. Now, I want to find out how much this area is going to be, and I want it in terms of radius. So I want A of r. My problem is this little h here. This h is in the way. I need to get just r's here. So let's talk about volume. Volume, find a spot here, of a cylinder is pi r squared h. In this case, the volume is 22. Therefore, h is 22 over pi r squared. Here's a case where I have to put one formula into another again. So my surface area in terms of r is 2 pi r squared plus 2 pi r times 22 over pi r squared. I can cancel my pi's, cancel one of my r's, and I'm left with 2 pi r squared plus 44 over r. And this is my final formula. So again, we took the surface area and wrote it in terms of r and h. I went back and used volume, which is pi r squared h, and wrote h in terms of r so that I could substitute in to get an equation for area, surface area, just in terms of r. We'll go over these together in class, and then we'll work on the homework. And that's it.